Yesterday we introduced this new concept of standing waves. We did a little demonstration with it, and we showed you what a standing wave actually is. Okay, we saw these standing waves occur when the string appeared to be standing still. The wave appeared to be standing still. Where did it come from? We know the waves weren't really standing still because in the end, they came from interference patterns. There was waves going one way through a string, waves going the other way through a string, interfering with each other, producing constructive and destructive interference. Most times, it looked like a random pattern. But every once in a while, when we hit the right frequency, the interference pattern produced this unique pattern, this unique shape that made it look like the wave wasn't moving, hence a standing wave. They only occur at certain frequencies, the resonant frequencies. This one would be the fifth one. Okay, standing wave where we have, okay, it looks like this. This would be the fifth one that would occur. We'll draw all the rest of them in just a moment as well. We're just drawing this one to show you the parts of it. The bump, where we have constructive interference, is called the antinode. This part right here that doesn't actually move, right? These parts are moving back and forth. The part right here that doesn't actually move, where we have destructive interference, is what we call a node. So the antinode, constructive interference, the node is where we have destructive interference. We drew some pictures yesterday of a string, something like a guitar string. A guitar string that was plucked and produced hundreds of different modes of vibration. But most of those hundreds of modes of vibration just died out. They disappeared after a very, very short period of time. The only ones that remained, the only ones that you hear, are the standing waves that are produced in that string. This would be the first one bump or one antinode. This would be the second one, two bumps or two antinodes, three antinodes, and so on. You could keep going with this, and you're not going to get an infinite number of harmonics or numbers of bumps that are produced in your guitar string. I'm not sure, to be honest, where it would end. Okay, but in the end, you could draw out the theoretical possibilities of more harmonics or more bumps in these. This one's what we call the first harmonic. Okay, the first harmonic has a frequency or occurs at a very specific frequency. We're going to call the length of the string L. Okay, the length of the string is L. Now the length of that string is going to be half of a wave, right? We're going from equilibrium through a crest back to equilibrium. It's going to be half of a wave. This is going to be a full wave. This one's going to be 1.5 waves, or we're going to say 3/2 times the wavelength. This one's going to be 2 complete waves, right? If you trace that out, there's 1 wave, there's 2 waves. Now, let's rearrange it to solve for lambda. Becomes 2 times L, just L, 2/3 L. And this one becomes, this one should have been wavelength, right? 1/2 L. And then finally, we take a look at our wave equation that we learned a few days ago. V is equal to F times lambda. Rearrange it to solve for F. Sub in 2L for lambda, and we end up getting V over 2L. So if you've got a guitar string, or any other string for that matter, that's attached at both ends, and you pluck that string, you're going to produce a sound. Okay, the first sound that you hear will be the first harmonic. It will be equal to V over 2L. It'll be equal to the speed of the wave divided by 2 times the length of that string. Okay, we talked yesterday about how you can change that pitch. Okay, Tom said you can adjust the tuners on the guitar. That tightens the string or loosens the string. That changes the speed. If you change the speed, you change the frequency that you're going to hear. Okay, somebody else said we put a finger on a fret. Okay, you put a finger on a fret, changes the length of it. Change the length of the string, you're going to change the frequency that you hear. Second one, V over lambda or V over L. Third one, V over lambda or V over 2/3 L, which is the same thing as saying 3/2 times V over L. Third one, or fourth one, I should say, V over lambda or V over 1/2 L, which is the same thing as saying 2V over L. What's our pattern here? Well, if the first harmonic is F1, then the second harmonic that we see right here is what? This is 1v over 2L. This one is the equivalent of saying 2v over 2L. We could put a 2 in there, right? Same thing, right? 1v over 2L, 2v over 2L. The second frequency is twice the first frequency. The third one, if you look at this one, the third harmonic is 3 times the first harmonic. And the fourth one is 4 times the first harmonic. And so on and so on and so on. So it's easy. Once you got the first one, we went through the analysis of the other 3 here, right? But we don't really need to. Because once we have the first one, what can we do? Just multiply it by 2 or 3 or 4. We don't have to derive the equations 4 times. Let's take a look at an example that's not in our book. So we've got a 25 centimeter long string that's set in vibration. So maybe it's a guitar string. It would be a short guitar string. Maybe it's a ukulele string. Or, I don't know, some kind of mini harp or something like that. Maybe it's just a string that you've got attached at 2 ends. The speed of the wave through the string is 500 meters per second. What are the first 3 possibilities for harmonics? The first 3 possibilities. So in other words, what are the first 3 sounds that you hear from this string? Well, I said just a minute ago, you can derive the equation for all 3 of these, or you can derive the equation for the first one and then calculate the other 2. Let's draw it out here. This is the first harmonic. L is equal to 1/2 of lambda. Lambda is equal to 2 times L. F is V over lambda, or F is equal to V over 2 times L. All right, let's get the frequency of the first harmonic here, F1. It's going to be 500 meters per second divided by 2 times 0.25. 0.25 because it's 25 centimeters, got to convert it to meters, right? 500 divided by 0.25. Sorry, 500 divided by 0.5 gives me, I think it's 1,000. Is that right? Which we're actually going to round to 2 digits, 1.0 times 10 to the 3 hertz. So the first one that we would hear, the first sound that this guitar would make, this string would make, would be 1,000 hertz. Can anybody give me a lightning fast answer to the following question? What would be the second one that we would hear? Yep, 2,000 hertz. Right, it's twice the first one. Good, Liam. What's the next one that we would hear? Next one should be easy now after Liam gave me that one. Right, what's the next one? 3,000 hertz. It's 3 times the first harmonic, right? So all we really have to be able to do is get the first harmonic. We could derive the equation again for the second and the third, just like we did right there. But in the end, if we can get the first one, then we can calculate the second and the third one fairly easily. We got some questions to work on, but these are kind of different. These are just up on the board here. Give you a few minutes to work on those here. We'll see where we get.